Hello and welcome. In this video, we will explore definite integrals and their application to finding the area under a curve. This topic is a core component of the IB Mathematics Analysis and Approaches higher-level curriculum. By the end of this session, you will be able to, first, evaluate definite integrals using the fundamental theorem of calculus. Second, calculate the area of a region bounded by a curve and the x-axis. And third, find the total area enclosed by a function that crosses the x-axis. Let's begin by recalling the definition of a definite integral. The definite integral is a powerful tool for calculating the exact area under a curve. It's defined as the limit of a Riemann sum, but in practice we use the fundamental theorem of calculus to evaluate it. The theorem states that if f of x is any antiderivative of f of x, then the definite integral of f of x from a to b is equal to f of b minus f of a. Here, a and b are the lower and upper limits of integration, respectively. The notation with the square brackets means we evaluate the antiderivative at the upper limit and subtract its value at the lower limit. Let's work through a few examples to solidify this concept. Our first example is to evaluate the definite integral of sine x divided by the square root of cosine x from 0 to pi over 3. This integral requires a substitution. Let's choose u equals cosine x. The derivative of u with respect to x is negative sine x. Rearranging this gives us du equals negative sine x dx. Now we must change the limits of integration to be in terms of u. This is a crucial step in definite integrals. When x is 0, u is cosine of 0, which is 1. When x is pi over 3, u is cosine of pi over 3, which is 1/2. Substituting these into our integral, we get the integral from 1 to 1/2 of negative 1 over the square root of du. Notice the negative sign from our substitution. We can use the property that swapping the limits of integration changes the sign of the integral. So, this is equal to the integral from 1/2 to 1 of u to the power of negative 1/2 du. Now we can integrate. The power rule for integration states that the integral of u to the n is u to the n plus 1 divided by n plus 1. Applying this, we get u to the 1/2 divided by 1/2, which simplifies to 2 times the square root of u, evaluated from 1/2 to 1. Finally, we apply the fundamental theorem of calculus. We evaluate at the upper limit 1 and subtract the evaluation at the lower limit 1/2. This gives us 2 times the square root of 1 minus 2 times the square root of 1/2. Simplifying this expression, we get 2 minus 2 over the square root of 2, which is 2 minus the square root of 2. This is the exact value of the integral. Let's look at another example, this time involving a polynomial and a square root. We need to find the exact value of the integral of x times the square root of x plus 4 from negative 4 to 6. Again, a substitution is appropriate. Let's set u equal to the expression inside the square root. Let u equal x plus 4. The derivative du dx is 1, so du equals dx. We also need to express x in terms of u. From our substitution, x equals u minus 4. So x equals u minus 4. Next, we change the limits of integration. When x is negative 4, u is negative 4 plus 4, which is 0. When x is 6, u is 6 plus 4, which is 10. Now we can rewrite the integral entirely in terms of u. The integral becomes the integral from 0 to 10 of u minus 4 times the square root of u dt. To integrate this, we first expand the expression. This is the integral from 0 to 10 of u to the 3/2 minus 4 times u to the 1/2 du. Now we integrate term by term using the power rule. The integral of u to the 3/2 is 2/5 u to the 5/2. The integral of 4u to the 1/2 is 4 times 2/3 u to the 3/2, which is 8/3 u to the 3/2. We evaluate this from 0 to 10. Applying the fundamental theorem of calculus, we substitute the upper limit, 10, and subtract the result of substituting the lower limit, 0. The lower limit term is 0. Let's simplify the terms. 10 to the 5/2 is 100 times the square root of 10. 10 to the 3/2 is 10 times the square root of 10. So we have 2/5 times 100 root 10 minus 8/3 times 10 root 10. This simplifies to 40 root 10 minus 80 over 3 root 10. Combining these terms, we get 120 over 3 root 10 minus 80 over 3 root 10, which is 40 over 3 root 10. This is our final exact answer. Now, let's connect definite integrals to their most common application, finding the area under a curve. If a function f of x is positive and continuous on an interval from a to b, the area A bounded by the curve, the x-axis, and the vertical lines, x equals a and x equals b, is given by the definite integral of f of x from a to b. Let's visualize this. Imagine a graph of a function y equals f of x that stays above the x-axis. We are interested in the area of the region enclosed by the curve, the x-axis, and the vertical lines at x equals a and x equals b. The definite integral calculates this exact area. Let's see this in action with a simple example. Consider the problem of finding the area of the region enclosed by the line y equals 2x, the x-axis, and the vertical lines x equals 0 and x equals 4. We can solve this in two ways, using geometry and using integration. First, let's use a geometric argument. If we sketch the graph, we see that the region is a triangle. The base of this triangle is the distance from x equals 0 to x equals 4, which is 4 units. The height is the y value of the line at x equals 4, which is 2 times 4, or 8 units. The area of a triangle is 1/2 times base times height. So, the area is 1/2 times 4 times 8, which equals 16 square units. Now let's use integration. The area is given by the definite integral of the function from 0 to 4. So, the area is the integral from 0 to 4 of 2x d. The antiderivative of 2x is x squared. We evaluate this from 0 to 4. Applying the fundamental theorem, we get 4 squared minus 0 squared, which is 16. As expected, both methods give the same result. Let's try a more complex curve. Find the area of the region enclosed by the parabola y equals x squared plus 1, the x-axis, and the vertical lines x equals 1 and x equals 2. First, it's always helpful to sketch the region. The parabola y equals x squared plus 1 is always above the x-axis. The area we want to find is the region under this curve between x equals 1 and x equals 2. Since the function is positive on this interval, the area is simply the definite integral. The area is the integral from 1 to 2 of x squared plus 1 d. The antiderivative of x squared plus 1 is x cubed over 3 plus x. We evaluate this from 1 to 2. Now we apply the fundamental theorem of calculus. We substitute the upper limit, 2, and subtract the result of substituting the lower limit, 1. This gives us 8 over 3 plus 2 minus the quantity 1 over 3 plus 1. Simplifying the fractions, we get 14 over 3 minus 4 over 3, which is 10 over 3. So the area is 10 over 3 square units. What happens if the function is negative on the interval? Can we still interpret the integral as an area? If f of x is negative on the interval from a to b, the definite integral will be a negative number. However, area is always a positive quantity. To find the area, we must take the absolute value of the integral. This is equivalent to placing a negative sign in front of the integral. Visually, if the curve is below the x-axis, the integral gives a negative value. To get the positive area, we multiply the integral by -1. Let's see an example. Let's find the area bounded by the x-axis and the parabola y equals x squared minus 2x. First, we need to find the limits of integration. These are the x-intercepts of the parabola, where y equals 0. Setting x squared minus 2x to 0 and factoring, we find the intercepts are at x equals 0 and x equals 2. Now, let's sketch the graph. This is an upward opening parabola with intercepts at 0 and 2. The region we are interested in is the one enclosed by the parabola and the x-axis, between x equals 0 and x equals 2. Notice that this region is entirely below the x-axis. Since the function is negative on this interval, the area is the negative of the definite integral. Area equals negative the integral from 0 to 2 of x squared minus 2x dx. The antiderivative is x cubed over 3 minus x squared. We evaluate this from 0 to 2. Substituting the limits, we get negative the quantity 8 over 3 minus 4 minus 0. This simplifies to negative the quantity -4 over 3, which gives a positive area of 4 over 3 square units. What if a function crosses the x-axis within the interval of integration? In this case, we need to find the total area. The total area is the sum of the areas of all the regions, both above and below the x-axis. We must calculate each area separately and then add their absolute values. This means we need to find all the x-intercepts within the interval to determine where the function changes sign. For example, if a function f of x crosses the x-axis at c, the total area from a to b is the integral from a to c plus the absolute value of the integral from c to b. The first part of the integral represents the area above the x-axis, which is positive. The second part represents the area below the x-axis, which is negative. We take its absolute value to make it positive. Let's work through a detailed example. Let's find the total area of the regions contained by the function f of x equals x cubed plus 2x squared minus 3x and the x-axis. First, we find the x-intercepts by setting the function to 0. Factoring out x, we get x times the quantity x squared plus 2x minus 3 equals 0. Factoring the quadratic, we get x times x minus 1 times x plus 3 equals 0. The intercepts are at x equals 3, 0, and 1. These intercepts divide the x-axis into two intervals where the function has a consistent sign, from 3 to 0 and from 0 to 1. A quick sketch or test points show that the function is positive on the interval from 3 to 0 and negative on the interval from 0 to 1. The total area is the sum of the area of the first region and the absolute value of the area of the second region. Total area equals the integral from 3 to 0 of f of x dE plus the absolute value of the integral from 0 to 1 of f of x dx. Let's calculate the antiderivative first to save time. The antiderivative of x cubed plus 2x squared minus 3x is x to the 4th over 4 plus 2x cubed over 3 minus 3x squared over 2. Now let's evaluate the first integral. The integral from 3 to 0 is f of 0 minus f of 3. This gives us 0 minus negative 11 and 1/4, which is 11 and 1/4. Next, the second integral. The integral from 0 to 1 is f of 1 minus f of 0. This gives us negative 7 over 12 minus 0, which is negative 7 over 12. Finally, we add the absolute values. Total area equals 11 and 1/4 plus the absolute value of negative 7 over 12. This is 45 over 4 plus 7 over 12, which simplifies to 135 over 12 plus 7 over 12, giving a total area of 142 over 12, or 1 over 6 square units. Let's recap what we've covered. We started with the fundamental theorem of calculus, which provides a method for evaluating definite integrals. We saw that for definite integrals, it's essential to change the limits of integration when using substitution. We then established that the definite integral of a positive function gives the area under its curve. For functions below the x-axis, we must take the negative of the integral to find the positive area. Finally, we learned that to find the total area of a function that crosses the x-axis, we must split the integral at each intercept and sum the absolute values of the resulting integrals. You are now equipped to evaluate definite integrals and calculate areas bounded by curves and the x-axis, which are key skills for the IBAA-HL exam. To help you practice and master these concepts, here are 5 IB-style practice questions. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Evaluate the integral from 0 to pi over 2 of sine squared x times cosine x dx. Question 2. Find the area of the region bounded by the curve y equals x cubed, the x-axis, and the vertical lines x equals 1 and x equals 4. Question 3. Find the area of the region bounded by the curve y equals 1 over x squared, the x-axis, and the vertical lines x equals 1 and x equals 2. Question 4. Find the area of the region bounded by the x-axis and the curve y equals x squared minus 4x plus 3. Question 5. Find the total area of the regions enclosed by the function y equals x cubed minus 9x and the x-axis. Welcome back. Let's go through the solutions. For question 1, We use the substitution u equals sine x. The limits change from 0 and pi over 2 to 0 and 1. The integral becomes the integral from 0 to 1 of u squared do, which is u cubed over 3. Evaluating from 0 to 1 gives 1/3. For question 2, the function y equals x cubed is positive on the interval from 1 to 4. The area is the integral from 1 to 4 of x cubed dx. The antiderivative is x to the 4th over 4. Evaluating from 1 to 4 gives 256 over 4 minus 1 over 4, which is 255 over 4. For question 3, the function y equals 1 over x squared is also positive on the interval from 1 to 2. The area is the integral from 1 to 2 of x to the negative 2 dx. The antiderivative is negative 1 over x. Evaluating from 1 to 2 gives negative 1/2 minus negative 1, which is 1/2. For question 4, the parabola I equals x squared minus 4x plus 3 has intercepts at x equals 1 and x equals 3. The region between these intercepts is below the x-axis. The area is negative the integral from 1 to 3 of the function. The antiderivative is x cubed over 3 minus 2x squared plus 3x. Evaluating gives negative the quantity, 9 minus 18 plus 9, minus 1 over 3 minus 2 plus 3, which simplifies to 4 over 3. For question 5, the function y equals x cubed minus 9x has intercepts at x equals 3, 0, and 3. The function is positive from 3 to 0 and negative from 0 to 3. The total area is the integral from 3 to 0 plus the absolute value of the integral from 0 to 3. Both integrals evaluate to 81 over 4. The total area is 81 over 4 plus 81 over 4, which is 81 over 2. I hope these examples and practice questions have helped you deepen your understanding of definite integrals and their application to finding areas. Thank you for watching.